This lecture is about correlation. So when we're talking about correlation, we're talking about a relationship between two continuous variables. That's a crucial distinction that we make in statistics as opposed to common language. And a correlation can only be measured when you have two continuous variables, and they have to both be measured on the same subjects. So we could talk about a correlation between the height and the weight of the same people, or a correlation between the number of undergraduates and the amount of annual tuition at schools. We couldn't talk about, for example, the correlation between the altitude of the highest mountains in a continent and the number of tacos that are sold in the cities in that continent, because those two things are not measured on the same objects. We also couldn't talk about a correlation between the color of a country's flag and the system of government that it has, because those two things are categorical or discrete variables, and you can't compute a correlation between discrete variables. The other thing that you can't do with correlation is you can't measure associations that are not linear. I know that was a double negative, so let me put it another way. This relationship here, you and I would look at this and say, okay, that's a U-shaped relationship. There is some relationship between this X variable that my face is covering and this Y variable that we're seeing here. But the correlation math can only detect a straight line. So if we just did the negative part or the positive part, the correlation could see it. Because this is symmetrical, they would cancel out, and the correlation would see that there's no, it would look to it like there's zero correlation. So you want to look at your data before you just go and compute correlations, because if there's a non-linear relationship between your two variables, then your correlation computation will miss it. So don't do that. So the other thing, the real world thing that correlation measures is what we call association. It measures how much your Y variable differs from its mean when X differs from its mean. So if X is a little bit above average, do we expect Y to also be above average, or do we expect Y to be below average, or do we have no knowledge about Y? And you could get a correlation when X and Y influence each other directly, if you're looking at supply of an object, of a good, and its price at a given time, or if you look at the amount of volume that kids in an online learning class have in their earbuds and how much hearing damage they incur. Those things, there's a cause and effect relationship, and so you would see an association. However, you can also see an association when X and Y are both affected by a common underlying cause. So for example, if you are looking at how much ice cream is sold and how much crime there is in a town, you might see that they are associated. Or if you looked at the amount of piracy there is in a given year and the average sea surface temperature, you might see that those are associated. But that doesn't necessarily mean that eating ice cream is causing crime, or the appearance of pirates is lowering the temperature. So let's look at those graphs. So here is a murder rate measure from a bunch of different cities, and here's how much ice cream is sold at a bunch of, I'm sorry, these are all from the same city but in different dates. And they're scaled from 0 to 100. And so you can see that on days where there's lots of murder, there's also lots of ice cream. And on days when there's very little murder, there's very little ice cream. And so you could think that this means that either eating ice cream drives people to murder, or perhaps that after a murder someone needs an ice cream to calm down. But a little further research would suggest that warm days are days where more people are on the street shooting each other and more people are eating ice cream. And on cold days, people stay inside and shiver, and so they have less opportunity to slay each other, and they have less impulse to eat ice cream. So an underlying thing here is temperature. This is slightly cartoon data, but this is a real correlation you can find in the real world. Another classic example of correlation being association is the number of pirates that we see in a given year and the global average temperature. So you can see that there's a declining relationship. There is a relationship between these two variables. There's an association. And so the people who first posited this relationship said that they think that this is happening because pirates are cool, and so the more pirates you have, the colder the weather. But of course, a more sensible notion of association is that over here we have days with lots of years where there's lots of industrialization, so they are driving climate change with CO2 emissions, but they also have large, efficient navies that can drive pirates from the sea. And down here, not so much. Finally, correlation is unitless. What that means, it's like a percentage, right? Percentages, there's no units, so if you say there's a 50% increase, that could be talking about anything. So same with a correlation. A 0 means there's no association between the two variables. Positive 1 means a perfect positive association, so when x goes up, y goes up by a predictable amount. And negative 1 means a perfect negative association. For every bit that x goes down below the mean, y goes down by a predictable amount. And if your correlation is less than perfect, you can measure it with the coefficient of determination. So you square the correlation. So then it goes from 0 to 1. It's never negative because it's squared. And this is the proportion of variance in y that's explained by x and vice versa. So 1 would be perfect. 0 would be no relationship. So let's look at some pictures. So here we have that same correlation I showed on the first slide where there's a pretty strong positive relationship. You see there's still some variation. So this would have a high correlation, maybe in the 0.6 to 0.8 range. And so the squared correlation would then be in the 0.36 to 0.64 range. Whereas this one, this is a perfect straight line, so the correlation is 1, and the coefficient of determination is also 1. Here we have a negative relationship. This correlation is probably around 0.9, so it's negative 0.9, right? It's declining. So it's r squared would be about 0.8. So about 80% of the variation in x and y is explained by x and vice versa. I think that is the last slide. Nope, here's some more examples. So here's a weak negative correlation. This is a nonlinear relationship, but it still has approximately line-like shape, so negative 0.3. Strong positive 0.8, so we have r squared of 0.64. No correlation again, the U shape here, because the best fit with a straight line is about a horizontal line. And here's a strong negative, so it's the same strength as this one, but it's negative, so it's negative 0.8. So this would have the same coefficient of determination, about 0.64.